Looks good?
Yep.
Okay.
Awesome.
Great. All right,
Thanks
great. So a lot of what we do as researchers is we spend time arguing about the credibility of different research findings. Maybe even the majority of our time is spent doing that. And we do that because we disagree. And so why might we disagree about the credibility of a finding? We might have different methodological views, right? So some people might be more skeptical about observational studies than others. We might have different prior beliefs about certain parameters. So if we're trying to estimate a causal effect, we get some result that seems totally crazy, maybe we're going to be more skeptical about the credibility. These two are maybe sort of okay reasons for disagreement, but one that we might be worried about is that researchers might also have what we call directional motives. They might be motivated reasoners about their research findings, which might lead them to reason about whether a certain study is good and about whether causal effect is positive or not, for reasons outside of just the truth. So we're going to do sort of a quick theory and experimental test in this paper, hopefully. The theory is a really straightforward combination of first a paper that I wrote with Tom, and so I have links to these in the chat, where we sort of conceptualize how we should think about learning from a research design that might be biased, kind of as like a micro theorist would, and sort of building on the last panel, how I think a lot of people here think about this, is thinking about it as like a signal extraction problem. So whenever we observe an estimate from a study, that's equal to, say, the causal effect that we want to learn about, plus some systematic bias and plus noise. And so we can use, once we specify our priors, we can use Bayes' rule to determine how we should learn about the causal effect. However, we also might be concerned that people are motivated reasoners and might care more than just about Bayes' rule. And so another paper of mine has a way to formalize this, of treating motivated reasoning as solving a maximization problem, where you want to hold beliefs which are not sort of likely in your posterior belief, but also you may have a directional motive. You may like holding certain beliefs more than others. And what this formalization shows is that even sort of wanting to believe something about one variable might affect your beliefs about another variable. So what the sort of theory shows here is that if, say, you want to believe that a treatment effect is high for some reason, then you might conclude, sort of irrationally, so to speak, that the selection bias is negative, right? You might sort of want to find reasons to think the selection bias is negative to hold the belief that you want about the treatment effect while also having a coherent view. If we think about the credibility of studies as not just about the realization of the bias, but the variance in the bias, so a credible study might be one with a low variance in the bias, what you can get there is that you might conclude that a study is good in the sense of low variance if you see a result which is consistent with what you want. So if I want to see a high treatment effect, I might believe high results, but also reasonable in the sense that sort of results that are too extreme in one direction may always seem impossible. And not surprisingly, in the problem, you can just throw some weights on these motives, and these distortions are going to be increasing as we have more directional motives, decreasing as we care more about accuracy. And so the empirical strategy we want to use, and I can talk more about why we think this is the appropriate one, is to try and manipulate the magnitude of these two motives and then see how that affects the way that people respond to research studies, kind of in a way similar to the platform that was just discussed. So our sort of current idea for how to do this is to present people with a hypothetical study, saying like we're doing maybe something like a get out the vote experiment, where we go around sort of canvassing people about the integrity of elections, but maybe we only go in a certain time window. So there could be an external validity concern that we're only estimating the effect for people who are home at a certain time. So we kind of want to get at something that's like a minor, so to speak, concern that some researchers might weigh more than others. So then we're going to ask people, or we're planning to ask people, sort of, what do you think is the true average treatment effect? And also questions like, what do you think was the bias in that estimate, and sort of the quality of it? Is this sort of a design which will generally return a good answer? And so then to test our theory, what we want to do then is find ways to manipulate these weights. And so our sort of proposal for how we want to do this is first to maybe manipulate people's directional motive. We might sort of prime to them the fact that, you know, maybe a positive treatment effect in this study might help lower polarization. So sort of trying to convince people that it'll be a good thing for our democracy, such as it is these days, if we were to find a certain effect. To manipulate the accuracy motive, we might say something like, if the partner organization thinks this is going to work, they might scale it up. And that might make us sort of weigh those considerations more. So I'll sort of just stop there. We're curious for any feedback on this. Maybe, do you believe these manipulations will work? So we have some sort of other thoughts about, should we be doing a factorial? Should we vary the treatment effect? And then also maybe sort of like, who should our population be for this? Should we just be asking political scientists and economists, or should we be asking more widely? And so I will stop there. Thanks.
That was 5 minutes sharp. Thanks for being so timely. We have 1 minute for a question, if anyone wants to jump in. Okay. Well, I guess Andrew will be available to answer any quick questions in the chat and also in the Slack channel. Thanks, Andrew. Now we have Maya Mather next, who is an assistant professor at the Stanford Quantitative Sciences Unit and associate director of the Center for Open and Reproducible Science at the Stanford Data Science Institute. Without further ado, Maya, take it away.
Great, thank you. So the question that I'm going to be trying to address is, how severe is publication bias in meta-analyses of peer-reviewed studies? And we tried to address this empirically by doing a meta-analysis. So in the first step, we created a systematically sampled corpus of 58 large meta-analyses, which we collected from 4 different sources that we wanted to span a variety of different disciplines. The first was the Generalist Journal PLOS One. That was the majority of meta-analyses. Second, 3 top medical journals. Third, 3 top psychology journals. And fourth, an online open data repository of meta-analyses on developmental psychology. So there's various ways to think about publication bias. One that is intuitive and it kind of characterizes its magnitude well is as the selection ratio. This is the number of times more likely significant positive results are to be published than non-significant or negative results. I'll call the former affirmative results and the latter non-affirmative. So a selection ratio of 1 would mean that there's essentially no publication bias, no differential favoring. We use selection models to estimate the selection ratio for each of these 58 meta-analyses and then meta-analyze the resulting estimates. And here are the results. I'll draw your attention mainly to this first line, which is overall estimates for all 58 meta-analyses. This column eta hat is the average selection ratio across all of these, representing that affirmative studies were on average 17% more likely to be published than non-affirmative results. Importantly, the confidence interval crosses the null. And our first impression was that this seems like a result that was smaller than what we expected, somewhat less publication bias than we had thought. It is important to note that it varied substantially across meta-analyses. This column Q95 is telling you the 95th quantile of selection ratios and is saying that in the worst afflicted 5% of meta-analyses, affirmative results were favored by at least 3.5-fold over non-affirmative ones. This is further broken down by the sources, PLOS One, and the specific disciplines. PLOS One and top medical meta-analyses showed essentially very little evidence of publication bias. Again, on average, there were some outliers, but in general, there was relatively little publication bias. Top psychology was a little bit worse, with approximately a 54% favoring of affirmative results, and MetaLab, the developmental psych meta-analyses, actually had the most of all, with an average selection ratio of 4.7. Note that these are small samples in terms of the number of meta-analyses, however, within each category. The other thing we did is we tried to kind of do analyses that would not use as many statistical assumptions as are typically needed to estimate the severity of publication bias. So what we did here is we use sensitivity analysis methods that do not try to estimate publication bias, but rather ask how severe it would have to be, hypothetically, in order to completely explain away the results of a meta-analysis. These analyses found that for the large majority of meta-analyses, 90%, it would have to be the case that affirmative results were favored by at least 3.3-fold in order to explain away the results of that meta-analysis. Similarly, for 89% of meta-analyses, the amount of publication bias that would be needed to explain away the results was stronger than what we estimated was actually present in the vast majority of meta-analyses from that corresponding discipline. We also considered the impacts of hypothetical worst case publication bias, which would favor affirmative results infinitely over non-affirmative. And it turned out that the majority of meta-analyses could not be entirely explained away by even worst case publication bias. So this was somewhat less publication bias, again, on average than we expected. We did a couple of pre-registered analyses to consider whether there was maybe more publication bias in kind of super top tier studies, or maybe the first couple studies published on a topic. Neither of those seemed to pan out. In post hoc analyses, we looked a little bit at whether it could be that it's the headline results of papers, the ones that appear in the abstract, for instance, that have the most publication bias. And this actually did speculatively seem to hold. So overall, our take home is that we suspect it's the case that the mere act of doing a meta-analysis in which you're including kind of secondary findings or things that you calculated from statistics and tables, in addition to headline results, itself actually helps mitigate some of the publication bias that we see so much in the original literature. That's it. Copies of the papers are online, and you're welcome to contact me with more questions.
Awesome, thanks, Maya. We have a quick question from Sean Grant, who's asking, are these results of the overall meta-analytic estimates or the estimates of the studies included in the meta-analysis?
Yeah, great question. So we reanalyzed the studies included in the meta-analysis. And an important point that I didn't get to is that we actually used only the peer-reviewed studies. So some meta-analyses have unpublished studies. So we basically fit these selection models to the estimates that were meta-analyzed.
Awesome. Well, I think that's all the time that we have for this session, but I think there are two other questions that you could try to address in the chat.
I'll get them in the chat.
Okay, so next up we have Francesca Parente, who is a postdoctoral fellow at the Newhouse Center for Globalization and Governance at Princeton University. Francesca, you can see your slides. You can unmute yourself.
Yes, hi, thank you for that.
Awesome.
So this is joint work with Chad Hazlitt at UCLA. And what we want to do is advocate for a sensitivity-based approach to observational studies. So we often argue about whether an effect is identified, meaning is confounding bias exactly zero, and then present our results as if this strong assumption holds precisely. And maybe we conduct some tests that show that, our model is robust to various specifications that allow us to test about confounding bias, but we can't ever actually say, unless we have a really strong sign, that confounding bias is exactly zero. So we're advocating for what we call the sensitivity-based approach, which instead communicates how much confounding it would take to change the answer, and then aids users and readers in debating whether we can rule out confounding with that strength. And we support this approach because it's more transparent and allows us to precisely show what we must be prepared to believe in order to accept a research conclusion. So there are some simple statistics for reporting sensitivity. These come from Schnelly and Hazlitt's 2020 piece in the journal in JASA. But basically we have, the ones I want to present today are the robustness value, which is a single parameter that fully characterizes sensitivity. The RV, or robustness value, tells us what the point with equal association to treatment and outcome would eliminate the effect. So how much confounding has to be present with between the treatment and the outcome, or the confounder and the outcome, in order to reduce the effect to zero. You can also find this RV level for any level alpha. So perhaps we want to know not when the effect goes to zero, but when the effect would lose statistical significance. We can also talk about the partial variances explained by the treatment, which is best characterized as an sort of extreme scenario where if the confounder explained all of the residual variance of the outcome, R squared Y with respect to D given X tells us how much of the residual variance the treatment the confounders would need to explain to bring the estimated effect to zero. In the paper, we illustrate the usefulness of these sensitivity tools by analyzing the FARC referendum in Colombia. Basically, in the extensive published work on the FARC referendum, there are two hypotheses. One is that exposure to FARC violence led people to vote in favor of the deal. Another is that affiliation with President Santos led people to vote in favor of the deal. And so we estimated these models much like the papers did. And what we're suggesting is in a regression table that one adds these sensitivity statistics. So we have our estimate, our standard error, our t-statistic, and then we have these sensitivity values that illustrate how sensitive these results would be to the unobserved confounding. And so while, you know, these are conventionally significant, that the RV tells us is that the confounding that explains 6.1% of both the violence treatment and the outcome residual variance would bring the estimate to zero, but confounding that explains less than 68% of both the political affiliation treatment and outcome residual variance would not. We can also talk about the RV alpha, so and alpha equals 0.05, showing us that confounding that explains just 0.4% of the remaining variation in the violence treatment and outcome would bring the estimate to non-significance, but confounding that explains less than 66% of the remaining variation in political affiliation treatment and outcome would not. While there aren't really strict barriers on, you know, is 6% enough, is 68% enough, what we talked about in the paper is how you need to place, you can place bounds on these values to sort of suggest how plausible is this. So you need to, once you have these values, you can debate about whether or not this level of confounding is likely based on your own knowledge of the research design and also the context of the subject matter. So to conclude, we argue that sensitivity-based research practice could change what we study while being honest and careful about identification concerns, how we report results, because adding sensitivity statistics to regression tables communicates valuable information in a very simple way, and third, how we read, critique, and improve each other's work. So we can move on from a qualitative debate about whether or not an effect is or isn't identified to a quantitative one, which instead asks, how much confounding would it take to change the conclusion? You can install the SenseMaker package in R that produces these quantities or download it from the Shiny apps on Carlos's website. Thank you.
Awesome, thanks, Francesca. That was great. We have a question from Maya. Maya, would you mind asking your question?
Yeah, I think I'm unmuted now. Yeah, very interesting. I was curious whether this approach involves making any assumptions on the structure or nature of unmeasured confounders, like no interactions, binary variables, like the things that have kind of been tricky in the sensitivity analysis literature so far.
Yeah, so no, it does not make any assumptions about the form of confounding. We allow for the possibility of multiple confounders, ones that have different levels of strength. One of the things I didn't talk about are these contour plots that you can generate where you can say, oh, the confounding of this variable is of this strength and confounding of this other variable would be of this strength. What would happen to my estimate? The only thing I will say is that this approach from Chinelli and Hazlitt is really meant for linear regression only. And so that would be the primary limitation. But we don't make any assumptions about the form of the confounding.
Thank you.
Awesome. I think we can, if the presenters can stick around for 5 to 10 more minutes, we can open up the floor for questions to any of the 3 lightning talks that you guys just saw.
I think really quickly though, before that, if people do need to go, we'll just make a couple quick announcements. Those are that we'll start again tomorrow at the same time. So 8 o'clock in the morning Pacific, using the same link. So the link that Alex sent you in an email, we'll probably send another one this afternoon anyway, but just in case. And then also just a reminder that the Slack channel is open to continue talking if you can't stick around. So thank you, everyone.
Yes. So if there are any questions, either post them in the chat or unmute yourself and go ahead and ask your question.
Francesca,
I guess
can I
it
ask
was
you a
just a-
question then? Oh, go ahead.
Yeah, sure.
Yeah, go ahead.
I'm curious whether yours is, does it have a direct mathematical relationship to e-values, or it seems
So I
more-
mean, yeah, it is similar in the concept. I'm not sure. That would be a better question for Chad, who I don't think is here, about whether there's a direct mathematical relationship between those two. But I we're sort of in the same idea about having values that would allow us to communicate this information.
Yeah, your parameterization is nice. It's intuitive.